So what I wanted to do today also is to give you a little bit of history, and I won't go into too much detail or hopefully too boring of a scenario of history, but hopefully you'll enjoy this. I think it's kind of interesting to see the evolution because that's what allowed us to kind of get to where we are today. So if you look at the history of measurement, the basic unit of length was the pharaoh's forearm, right? The cubit was the tip of the elbow to the tip of his finger. Well, they couldn't take the pharaoh everywhere. They needed to measure something, and after a while that kind of got kind of boring for him to do that. So they would make a rod or a standard, and they would take that standard. I don't know exactly how they measured it, but they had to just kind of copy the one before that, and then they would have those spread around, and they would keep those in temples, right? So they would keep those in the sacred place or a place where something of great value was kept at, and so they would keep that rod and bar in a temple. And these days, our temple of measurement is called NIST, right? National Institute of Standards Technology. And from the cubit to portions of a micron, we've evolved tremendously over the years. So as we go back from the days of the pharaoh to circa 1865, this was a gauge that was used in one of the British Standards Institutes. And the instructions to the operator were to place the rod snugly between the end stops. And for years we've been trying to understand, what does snugly mean? It's open to interpretation, right? It's very, very rough. But at least it was something. We had a gauge. We had a way of identifying the length of something and what it was. And we kept getting more precise over the years. So fast forward to the early 1900s and the advent of the optical comparator. So now what we started to do was we started to image things. So we started using the power of optics to image things. Many of you have probably used optical comparators, right? So you know what an optical comparator is. What does that help us do? It helps us resolve fine detail so that we can be more effective in making a measurement, because it takes away some of that subjectivity. So advanced to 1960, and this is actually one that we've got in our lab. We keep it for history's sake. About 1960, Jones and Lamson was the inventor. And fundamentally, that comparator has not changed much, right? We still have lenses and we have a mirror, and we're reflecting that image onto a ground glass screen and magnifying that by the power of the lens. And so we'll typically take an overlay, we'll put that on the screen at the power of the lens, and we'll compare it, right? So that's the comparator function. But what does today's technology offer us? So there's that comparator. This is a modern day comparator, and it's a lot more powerful, right? It's got linear encoders on it, where we're down to the micron or half micron. We have the ability now to move that part around the stage and optically determine an edge by using a fiber optic edge sensor to get the edges. I'm sure many of you are familiar with that. And then now the readouts have gotten more sophisticated. We got PC readouts and all the power that the PC brings to the process, where you can network your data, you can store files, you can call up measurement routines. And then some systems are also have motion control, CNC control. So now you can actually do repetitive measurements on parts that you measured once. Well, the next time you go to do it, you don't need to just do it manually. You could run it automatically. And size of comparators is all over the place. We have some machines that we make where you can literally walk into the back of the machine. And sometimes that's necessary when you have to clean mirrors and service the machine. So they're huge, up to 60-inch screen size. And then some, we've also added video optics, so we can actually take the power of video to help in resolving and making finer measurements. So one of the big keys in optical metrology is the Mylar overlays. How many of you use Mylar overlays on a comparator? Okay. Are they ever trouble? Are they ever challenging? Or they get dirty, they get torn, they get lost. When the drawing gets revved, the Mylar's got to get revved. So there's a cost associated with maintaining those. So what has happened over the past few years is the advent of using the DXF file, the design file, to actually project that onto the screen to compare the actual part. So now we're not relying on that overlay. And if you've ever used an overlay, sometimes it's very, very hard to determine where something's in or out. It's just a subjectivity, it's a trained operator. So the DXF file gets rid of the Mylar overlay and gives us some ability to have more flexibility than just what the Mylar overlay gives us. So that eliminates that subjectivity, and we don't have to store and maintain Mylars anymore. So that helps the process move along, and it's a savings as well. And today's technology, video comparators. So now instead of taking that image off that telecentric lens and bouncing it off of a mirror and putting it onto a ground glass screen, we're taking that image, we're putting it off of a CCD array, and that's going into the computer. We're processing that image, and now we can see that image on the screen. Now we can project that CAD overlay. We bring it into the screen, and we can see it. I don't know if you can see the red line there. That's just actually a picture of a razor blade or a drawing of a razor blade. And we can actually see that section. Now the beauty of the DXF overlay is it's not limited to just what you drew on your Mylar overlay, because that entire DXF overlay will track through with the part. So as you move your part across the video screen, the DXF tracks with it, and you can zoom in on it or you can back away. So it's very powerful.